In this video, we're going to determine the electric field from the electric potential. So let's consider that we have an electric potential, which is a scalar, and it's given by this contour plot. Now this contour plot can be represented by the scalar function v of x, y, z, that's equal to x squared plus y squared plus z squared. Now the question is, how can we get the electric field from this? Previously we considered a line going from A to B, and what we did is, to obtain the potential, we took the line integral of the electric field with the infinitesimal displacement vector dl. So we had v is equal to minus the integral from A to B of E dot dl. Now what we're going to do is we're going to consider 2 points along this line which is separated by dl. So dl is your infinitesimal displacement vector, and we're going to consider just 2 points. We then obtain the following differential form, which is dv is equal to minus E dot dl. Now, in Cartesian coordinates, which is x hat, y hat, and z hat, the electric field can be given by the various components. So we'd have the electric field is equal to E x hat plus E y hat plus E z hat. And as we saw previously, our infinitesimal displacement vector dl is given by dx x hat plus dy y hat plus dz hat. Therefore, what we can do, we take the dot product of E dot dl, and what we're going to obtain is dv would be equal to dot dx x hat plus dy. What this comes down to is, since we have x hat dot x hat is equal to 1 and x hat dot y hat is equal to 0 and so forth, what we have is ex dx plus ey dy plus ez dz. So now what we can do is we can define the directional derivative for each of the directions, x, y, and z. So essentially we're looking to see how much something changes in those directions. And what we're going to have is dv will be equal to dv with respect to x. How much does that change in the x direction? dx plus dv dy. So these are partial derivatives. dy plus dv dz dz. So essentially, this gives us the rate of change of our scalar function in the x, the y, and the z directions. So therefore, if we go back to our equation, what we can then do is we can write the components of the electric field out. So we'll have Ex is equal to minus dv over dx. Ey is equal to minus dv over dy, and Ez is equal to minus dv over dz. So we can put this all together by using the gradient operator. So we're using our del. So del, the gradient operator, is equal to minus d over dx x hat plus d over dy y hat plus d over dz z hat. And we can put this all together in order to obtain our electric field. So we had our electric field for the Cartesian coordinates was equal to x hat plus y hat plus z hat. That then is just equal to the gradient of our potential. So we have minus dv over dx x hat plus dv over dy y hat plus dv over dz z hat. So the gradient essentially operates on a scalar function to produce a vector whose magnitude is the maximum rate of change of that function at a point of the gradient, and it is pointed in the direction of greatest rate of change. So what we have just obtained is our electric field is equal to minus the gradient of the potential. Now, what does it mean to have the negative sign? Well, physically, it implies that if the potential increases as a positive charge moves along the same direction, so let's say x, then what's going to happen is you can have some non-vanishing component of the electric field in the opposite direction. So, for example, in the case of gravity, if the gravitational potential increases when a mass is lifted some distance h, the gravitational force must be downwards. So if we go back to the scalar potential that we had, you have Vx, y, z was equal to x squared plus y squared plus z squared. To obtain the electric field, what we do is just take minus the gradient of that potential, so that scalar function, and that's going to be equal to minus 2x x hat minus 2y y hat minus 2z z hat, and that is our electric field. And if we were to plot it, we would obtain a plot which looks something like this.